Autopilot off.
Land.
Landing dive phase. Landing flare phase. Touchdown. Touchdown
Right now,
cutoff.
you are seeing the simulation running live. Later, I will show you the same physics again as offline renderers from exported trajectories. It still comes out of the simulator, not from hand key animation. If you watched my previous video, this is the next step in the same thread. That one was the entry point. This is here to explain the mechanics, what has advanced since then, and some of the problems that showed up once the stack had to work as a whole. The rocket is listening, answering back, and executing real commands in the same physics world where the neural networks fly it. The voice layer is not the intelligence of the rocket, it is the interface. The flying still comes from small trained policies that receive sensors' numbers and output thruster commands. What you see here is still not the intelligent agent I want to build. I will be very ambitious about that direction next. For now, the next point is a small physical system where behavior can be trained, inspected, broken, repaired, and eventually selected at runtime. After SpaceX landed Falcon 9, a lot of people started making rocket simulations, so I'm not claiming this is a brand new idea. Long term, I still want to take this further than the landing demos I have seen, especially once the agent layer is serious. I am not a rocket expert, and this is not a real rocket project. What I care about here is that the system is physical. When the controller is wrong, the failure is obvious. It does not fail quietly. It falls, it turns, it hits the ground. The simulation is bullet physics. The rocket body is a rigid body. The legs are rigid bodies, and the joints are all constrained. The policy does not get to cheat. I do not inject new velocity to move it where I want. The only way the rocket moves is through external forces from simulated engines, thrusters, gravity, contacts, and constraints. If it builds too much angular speed, it has to recover from the same engines and legs that created the problem. To better visualize, I export the exact simulation trajectory into Blender. That means the Blender render is not hand animated, it is a replay of what happened in the physics engine. I can look at a crash frame by frame and ask a very specific question. Did the policy make a bad decision, or did the reward teach the wrong lesson? Hover looked solved for a while, but it had a hidden problem. The policy was trying too hard to hold an exact altitude. If the rocket drifted a bit above the target height, it sometimes tried to correct too aggressively. That correction could tilt the rocket, and once the rocket had angular inertia, the rest of the flight became a recovery problem. The strange part is that this was not a control problem in the usual sense. I did not need a new actuator. The rocket already had the engine gimbal, leg thrusters, and leg angle. The issue was the reward. I was rewarding altitude precision too much, and stability not enough. So I changed the idea of hover. It is no longer hold this exact altitude at all costs. It is now closer to step upright, stay calm, and remain inside the healthy altitude band. Being a little high is not too dangerous. Being low is more dangerous. Trembling is worse than both. That small change matters. The policy should not dive back to the exact target height like the nervous pilot. It should protect the altitude of the rocket first, then gentle correct altitude. Here's the new mental model for hover. The simulated rocket has a target altitude, but around that target there is a slack zone. Inside that zone, altitude is considered healthy. The reward does not come push hard up or down. It mostly rewards the rocket for staying vertical, keep angular speed low, and not drifting sideways. If the rocket is above the band, it is allowed to descend slowly. If it's below the band, it should climb, but still without throwing away stability. This is the kind of detail that is easy to miss in reinforcement learning. A reward can be mathematically correct and still teach bad behavior. Be at this altitude. Sounds reasonable, but if the policy learns to chase that number too hard, the rocket becomes less safe. The reward has to describe the behavior we actually want, not just the number we want to see. This is the hover policy as a neural network. It could be smaller than people usually imagine when they hear AI. It is just a compact policy network. It receives the observation vector, passes it through a few hidden layers, and outputs the action vector. The observations are things like body frame velocity, angular velocity, the body up vector, rate distances, fuel, contact state, and actuator state. The policy does not see video frame. It does not know what it is a rocket in the human sense. It only sees numbers that change over time. The output is also just numbers: main throttle, gimbal pitch, and yaw. Leg thrusters, leg angle, those numbers are turned into forces and joint commands inside the physics simulator. Every policy uses the same kind of action vector. What changes is the behavior encoded in the weights. This is why visualization helps. Looking at the network does not magically explain every decision, but it makes the system feel less mysterious. There is no cloud service here, no hidden language model deciding what to do. It is a small function running locally, trained inside the simulator. The hard part is not running the neural network. That part is fast. The hard part is shaping the training problem so the behavior that emerges is useful. I have seen that many times in this project. A landing policy learned to hover near the pad instead of touching down, because the path toward the landing paid too much compared to the final landing itself. A target landing policy learned to arrive near the ground and then try to drift sideways towards the target, which is funny to watch but inefficient and unsafe. The lesson is that reward design is not just adding points for good things. It is deciding what should matter first. For the simulated rocket, the order is usually step upright, control angular velocity, manage speed, then worry about exact position. At the end of the system, I do not have one giant brain. I have a stack of small policies. Hover keeps the rocket stable, dive handles high altitude descent and recovery, land handles the approach of the pad, touchdown handles the final contact. Then there are target-aware versions of those policies, which receive 3 extra numbers: target offset in the rocket's body frame and the horizontal distance to the target. I like this structure because it gives me room to build a smarter selector later. Instead of asking one neural network to know everything, the system can choose the policy that matches the current situation. If the rocket is high and falling, it should not use the same behavior as the rocket that is 1 meter above the ground. If a target is selected, the descent should care about X and Z much earlier. If the rocket is close to the ground and unsafe, eventually I want a rescue policy whose job is to get away from the ground and stabilize. The voice system is separate from the flight intelligence. When I speak, the microphone audio is captured locally. A voice activity check waits until I am actually talking. Then Whisper converts the audio into text. After that, the app normalizes the phrase and tries to match it down to a known command. This is not a language model flying the rocket. That is important. If the rocket is falling, the voice layer can still be forgiven. If it hears something wrong, the HUD can show what it understood and the closest command, but execution still goes through the normal command parser. The rocket also talks back. That part uses Piper for local text-to-speech. The simulation creates a short status message, rewrites into something better for speech, and Piper turns into an audio. This created a funny problem. If the rocket speaks while the microphone is listening, Whisper might transcribe the rocket's own voice as a new command. So the app temporarily mutes the microphone while the rocket is speaking, waits a brief moment, and then restores the microphone to its previous state. It is a small detail, but it makes the interaction feel much more solid, though this requires fixing. The Blender pipeline is how I inspect the behavior outside the real-time app. The simulator records the rocket pose, leg pose, velocity, angular velocity, policy state, target state, and sensor state over time. That becomes a compact trajectory file. A Blender script reads it and builds the scene as an animation. This lets me use Blender as a debugging and visual tool, not just a renderer. I can make it a nice image, but more importantly, I can review exactly where the policy failed, where the target was, what phase it was in, and how the rocket was moving. The render is prettier than the OpenGL, but the motion still comes from the physics simulation. This project started as a toy rocket simulation, but it has become a small lab for learning how physical AI systems behave. The exciting part is not that the rocket lands once. The exciting part is that I can see why it lands, why it fails, and what kind of training pressure changes the behavior. There is still a lot to improve. Target landing is not solved yet. Hover had to be redesigned. Rescue is still a new idea, but the system is becoming more honest. Every failure gives me information, and every fix makes the next policy less fragile. One reason these projects move slower than it probably should is that I enjoy playing with the simulator too much. I run it, I try commands, I watch it fail in some new way, and then I go back and retrain or change the reward. I have already gone too much further than was strictly needed for the next stage. But sometimes I cannot help it. It is just too fun to test. That is what I wanted to show you in this video. Not just the rocket landing, but the loop behind it. Simulate, train, inspect, render, adjust, and then train again. It is groundwork for the more intelligent agent I want to tackle next. Thanks for watching, and consider subscribing.